Hi, welcome to linear regression. Regression is one of the mathematical tool for the problem of approximating the real valued functions. The linear regression is used as a statistical tool to perform the quantitative analysis of given problem statement. It is a predictive modeling method to investigate the mathematical relationship between independent variable x and continuous dependent variable y, and the given data is related by using the linear equation y equal to mx plus here mx plus c. Predictor shows the changes in the dependent variable when the changes in the explanatory variable in x-axis. That means when you are changing the values in x-axis, how it is affecting or impacting the changes in y. When you are substituting the values for x, different values of x, automatically y value also will change. It uses the current information about the particular phenomenon to predict its future behavior, which is involving graphical lines like a scatter plot uh, over set of data points that mostly close towards all the samples. For example, when you are creating the data samples for with the decision boundary will be close to all the data points, and which is using the data set when the data form a set of pair of numbers which is interpreted as observed values of an independent variable uh, and a dependent variable y. So here the independent variable is having other terminologies like observed values in the sense entire row is called observed value. There we are having the independent variable x, that is also called predictor and also explanatory variable. So three different terminologies they will use to represent the independent variable and also predictor and explanatory variable. The dependent variable y will be called as a response variable and also dependent variable. And the data model can be expressed by using the linear equation for simple linear regression. The straight line equation is used to represent the linear regression with continuous variable. Why it is called continuous variable? In the sense, here the continuous variable, the y value will have floating point numbers, the dependent variable will have floating point values. So this linear regression always will have continuous values with the floating point data type. That's why it is called continuous variable, and the relationship between the variables is represented by using the linear function y equal to mx plus c. The linear equation representation with single feature is given for machine learning model. Here for the machine learning model, instead of c we are using the theta 0, and instead of m we are using the theta 1 into x, plus small error will be available whenever we are applying the machine learning model to each and every data point. Here the theta 0 is called y intercept. So this place y intercept theta 0, and slope is represented by using the theta 1, which is given here. The slope for each and every data set, and the error, small error will be available for every data set whenever we are applying the machine learning model. X is the explanatory variable or independent variable or predictor variable. Y is called response variable or dependent variable. So this equation can be transforming into the predictive model, that is hypothesis of x with respect to the parameter theta. Y dash in the sense predicted output. Y is here, this is linear equation is converted into machine learning model equation. Here y dash in the sense predicted output equal to hypothesis of x with respect to the parameter theta is is calculated by using the theta transpose x. X represents the feature value of given data set. The this one, this x independent variable, and theta is the slope which is represented by using the parameter theta in linear equation. And we can show different relationships based upon the decision boundary which is drawn in the plot. When the data points are close to the decision boundary, then we can say the data are having a strong relationship with that is y variable and x variable. The dependent variable and independent variable both are having strong relationship in this data set. This is actually the decision boundary. This line is called decision boundary. This decision boundary is called positive decision boundary, and the below one here, which is called negative decision boundary. Here again the data is very close to the decision boundary, that predicted value. These are all predicted values of data points. The predicted values are very close to the decision boundary. That says the dependent variable is very strong relationship with x independent variable. And when your data points are very far from the decision boundary, so this is the decision boundary, here the data points are far from the decision boundary, then we can say this is showing weak relationship between the dependent variable and independent variable. Again, this is the negative decision boundary. So here also the data points are far from the decision boundary, so it shows the weak relationship between the independent variable and dependent variable y. And when your data points are far from the decision boundary, and also you see this is having horizontal line, here the single y value. So here for example, this y value is not at all changing. You look at that, it may be a 2, so this may be a 1, so 0. So when you are changing different x value, this the y value is not at all changing. Y value is, that is when you are applying the y equal to theta 0 plus theta 1 x1, here when you are changing the x1, different x1, but the y value is not at all changing. So this kind of plot shows there is no relationship between independent variable x and dependent variable y. And here the data is, even though close to the decision boundary, but there is no change in the y value when you are changing different x value. So there is no relationship between the x and y. The linear regression, in the sense, the dependent variable should change whenever you are varying the x value, but here no change in the dependent variable y. So there is no relationship between the uh, uh, independent variable x and dependent variable y. The plot shows the decision boundary calculation for each and every data point. Here the equation is y dash equal to hypothesis of x based upon the parameter. So this is given as a theta transpose x. It can be written as, here we are having only one dependent variable x, so we can say this is theta 0 plus theta 1 x with some error, right? So now this is the data point. Each and every data point we have given in the data set. We have given in the data set. So the decision boundary is drawn uh, for calculating the predicted value for each and every data point. So here the least square method can be used for calculating the uh, loss between the each and every data point. So you look at here, when you are taking this data point, this is the actual value of data point, and but our predicted value y dash is this one. So this is actually called y, the independent variable y. This is actual data given in the data set. Okay, in the data set, suppose if you are having the data set like this, so here x and y are given. So this value, for example, this may be a 3, this may be a 1. So here the x value is 3, y value is 1. So this is the data point 3 comma 1, for example. But our predicted value for this particular data point y dash, here we have got from our linear regression machine learning model, y dash is placed in this position. For example, this may be, for example, y value is 3. So predicted value is 3. So there is the error between the actual value and predicted value. So here the actual value is 1, predicted value is 3. The difference between this predicted value and actual value is called error. So this is the thing, this is called loss, this is called loss. So error can be calculated, but that is represented for epsilon of the ith data. This is data number 1. Actually I is representing the sample number. So this is for yi minus yi dash, right? So here estimated value is the this one, predicted value minus actual value is actual value of given data point. So here the estimated value is 3, actual value is 1. So the error is 3 minus 1, 2. So 2 units of error we got for this particular data point. So this is called loss of this particular data point that we have given in the data set. And here we will use two terminologies, loss function and cost function. Here when you are taking the loss function, it is the error calculated for the individual data points, but when you are calculating the error for all the data points, that is called cost function. So here that data set is having 3 data points. So in these 3 data points, when you are applying the average of these 3 samples error in the data set, that is called cost function. The cost function can be calculated for the given 3 training samples data set, 1 by 2m. M is the number of samples. Here number of samples are 3. Then summation of I equal to 1 to m number of samples, m is 3. Here the error between the predicted value and actual value, this can be represented y cap also sometimes, right? So the predicted value represented by using the y cap also. So y cap of ith sample minus yi whole square equal to 1 by 2m. This is sometimes represented the predicted value as hypothesis of xi. So xi means the x is the independent variable value, I is the sample number. I is the sample number. This is 1, 2, 3. I equal to 1, 2, 3. So 3 samples are there. So why we are squaring of this value, in the sense, you look at that. Suppose my you take this first data sample. First data sample estimated value is 2.9. The predicted value is 3.1. So 3.1. The difference between these two is minus 0.2, minus 0.02. Okay, so when you are minus 0.2, so when you are applying this, what will be happen? You are getting the negative value. We cannot say error in the negative value. So what we are doing, we are squaring up this value. When you are squaring up this value, you will get 0.04. So you will get the positive value. So always error to be represented in the form of negative value. So that's why we are squaring up by using the formula least square method. The least square method is here. We will apply the actual value minus predicted value whole square. Right? You can write like this also: predicted value minus actual value whole square. So both are similar only. So when you are squaring up, the negative value will become positive value. Thanks for watching.